Has everybody got that entered in? Graphed. So what are some of the key characteristics that you guys notice? So it first asks for the x-intercepts. So where might those be? At 2. And at -3. So we have 2 x-intercepts at 2 and at -3. Are they the same type of intercept? Or do they act the same? If you look at the graph. What at -3, what happens to the graph? We start below the x-axis and we go through the x-axis, right? It crosses. And then it goes, what? It goes out of range somewhere. We'll deal with that later. All right, then it has to come back. And then does it cross again here at this x-intercept?
That's not what it looks like.
3. How are the factors related to the x-intercepts?
The inverse.
Yeah. If solved, we find intercepts. Which means if you look at it in its current form, it is the opposite sign, right? I don't love that, but I do like this. If solved, set the factors equal to 0 and solve. Okay, change this. This next question should say x equals 2, and this should say x equals -3, not -2. We kind of alluded to this. What's different about the behavior of the graph at x equals 2 and x equals -3? Even though they are both x-intercepts, they have different behavior. So at -3, we cross, comma, at 2, we bounce. When I said we, I feel like I've got possession of this. Why? Well, how can I see? So again, all these forms are good at showing us different things. Like I showed you standard form was good at talking about y-intercept, talking about the degree. Factored form was good at talking about x-intercepts. So we're focused now on x-intercepts. So look at the factored form up there. Do you see anything that stands out for why we might cross somewhere and bounce at a different one? Correct. Because of how many times that intercept occurs, right? Right here, the intercept 2 occurs twice. So it has what we call a multiplicity of 2. If we can start talking about that. But even multiplicity bounces, right? Think about, we just got done looking at vertex form of a quadratic. So if this was my parent function, right, what happened? We shifted right 3 with a vertex. So where's the x-intercept here? The x-intercept is at 3. And it bounced off at 3. Because this is really just x minus 3 times x minus 3. Which means I have a x-intercept of 3 happening twice. Which made it bounce at that x-intercept. Okay? If the x-intercept occurred only once, it crosses. So the way they word it is they say happens twice. So it is like a quadratic. I don't love that explanation. I like what I said better, right? I mean, it's the same idea.
It's got the multiplicity.
Right. That's what we're fixing to get into, is using that word multiplicity. All right, let's look at the graph and talk about some of the vocabulary here. So at this point, we go through, and at this x-intercept, we bounce. All right, what are some other things we could talk about this graph? Thinking about what we did yesterday. When I first start with a graph, is what about its concavity? Concave down. When does it stop being concave down? Somewhere right around 1, right? And then it's going to switch to being concave up the rest of the way. So right here in purple, we have concave up. And in blue, we have concave down. All right, we have a y-intercept that's at 12. And I know that we didn't look at this in great detail, but the y-intercept is like here. And the max is actually a little bit to the left of that. So is that, what kind of maximum is that?
Relative.
Relative max or a local max? It's not the absolute max.
Wait, which one's right? Oh, yeah.
It's a relative or a local. What would be the absolute max of this graph?
Infinity.
That's right. It's going up forever. So it doesn't, its absolute maximum would be infinity. And then right there where we bounced, that would also be a relative min.
What is local?
Means the same thing as relative. It's interchangeable. Depending on the textbook, they might use different wording. Just like x-intercept, 0, and root. All are the same thing. The fancy way, so let's talk about this. I don't say this a lot, but we probably should. Right here at this x-intercept, I use this terminology. I say it bounces off the x-axis. Another way you could say that is it's tangent to the x-axis. Right? Think about what a tangent line is. Tangent line is something that touches the graph once. And so the tangent line at this point would be the x-axis. Right? Because it would have a slope of 0 fixing to be turning. So just making you aware of that, I do remember on a practice test last year, they used that terminology where they said it's tangent to the x-axis. And my kids didn't know what that meant. All it meant was it bounced off the x-axis there. Right? They're interchangeable again. So just knowing that. All right, let's look at 2, and let's see what we can figure out without graphing it, okay? Using what we just learned. So I've got x minus 2 cubed times x plus 4. So where are the x-intercepts at here? At 2 and negative 4? Could we find the y-intercept?
No.
Yes, if we...
We can. So just, how could we, let's do b first, because I think we could do that one kind of easily. What's the degree of this polynomial?
4.
It's degree 4 polynomial. Because I've got x minus 2 cubed, which means I would have an x times an x times an x, right? And then another x in the x plus 4. Makes it be degree 4. So, because I didn't care about all those middle terms to find the degree, do I care about all those middle terms for the y-intercept? What do I care about for the y-intercept? The constant term, the last term. So how can I find the last term? Just multiply the last in each one of these. So negative 2 times negative 2 is 4. Times negative 2 is negative 8. Negative 8 times 4 is Negative 32. So I can identify the y-intercept.
We're learning today.
Well, we're done with the intro stuff. This is it. This is the real deal. Polynomials, baby. That's where it's at. Like it or not, it's pre-cal time. Questions here about any of that? All right. So because it's degree 4, I've kind of already talked about some of this with you. Well, no, never mind. Let's make predictions before we graph it for what we think is going to happen at the x-intercepts. So let's start here with negative 4. What do you think is going to happen at negative 4?
It's gonna go through.
It's going to go through, right? It's going to cross at negative 4. What's going to happen at 2?
It's also gonna go through.
All right. So this time 2 has a multiplicity of 3, which is an odd multiplicity. So it is going to go through. Straight through that's an odd way to put it. Let's graph it. Let's graph it and see what it does. Because I don't think the terminology straight through is going to be applied anymore. I think you're going to like what it does. I think it's going to make sense to you when you see what it does.
Okay.
But I don't know about straight through. Can you see it? Or do I need to work on y'all's graphs again? So
I'm gonna say it goes straight through.
at negative 4, it does go straight through. Oh, you got something jacked up. You don't even have the other x-intercept.
And then
At 2, it goes through, but when you say it goes straight through, it's kind of like a. What does that remind you of?
one of them that I don't know. Is it?
What did I do wrong?
Does it remind anybody of like a cubic function?
Yeah.
Like how x to the third Gary's through snakes, right?
No.
Well, that makes sense that it would snake through because it's a third degree multiplicity, which fits because when it was a second degree multiplicity, it bounced like it was a quadratic, and that's a third degree factor, which means it's going to snake through. What if you did a fourth degree?
It would bounce.
It would bounce. It would bounce.
Um,
So when we graph this, can you guys see the y-intercept very well? You're missing lots of the graph here, right? If you're on that standard zoom. So let's expand our y value some.
is it straight?
So let's go from 100 to negative 100 instead of 10 to negative 10 on the y. X's are fine. Let's change the y scale. So I'm going to make this 100. I'm going to make this negative 100. And then I'm going to look at y'all's graphs. I know at negative 32, I need a y-intercept, which would be like right in. That's 22, Cody. Have you got yours to graph yet? Have you got yours to graph yet? Okay. Well, I knew you had a line earlier. I have x-intercepts at 2 and at negative 4. And so for me, I know the graph starts up here, ends up here. I know it snakes through here. I know it crosses here. But that's all I know without looking at a graph, right? Like I can identify all that without the graphing calculator. But now to get it looking more exact, I would have to look at what you guys have graphed. And it's going to go, it even still goes off the screen, doesn't it? Wow. So we're still going beneath negative 100 somewhere. And then turning, and then we're crossing, we are snaking. That's a rough estimate, right? So when we graph these polynomials by hand, you see how I graphed it using some key characteristics. Like, I didn't know it, like, I don't know where this turning point is. You guys don't know exactly where it is either, but you could find it if you kept zooming out, right? But I mean, I have no idea where this is without a calculator. I know where this is. I know that this and this, right? I know it crosses here and it snakes there. This should be at 2. It's close.
Such a sus graph.
But that's all I know. It's sus? Why?
Because if you count 1, 2, 3, it only changes 3 times, but it's degree.
What only changes 3 times?
The slope.
Well, let's see. We go from, it's concave up, right? Concave up. Then it, somewhere in here, it has to switch to concave down, right? When it snakes through. I don't know exactly where, again, I don't have it. But it's going to switch to concave down, and then it goes back to being concave up. So it changes concavity 3 times
But it
for a
doesn't,
degree.
it doesn't change, not all the way down, just half.
You don't like it because this doesn't, you don't get a local max, is what you're saying. You got a local min, and that's it,
Yeah.
right? This is not only a local min, actually, this is an absolute minimum. Okay.
That's fine.
Let's find the absolute minimum. You could.
I don't have to.
Yeah, go for it. So we know what's the x-intercepts here. It crosses at -4. It ain't going to be that big, is it? Just a little over -100?
Negative 200.
The minimum? The graph that they made here disagrees with that. I'm not telling you you're wrong. I have to look at yours. Crosses at -4, and I'm going to say it snakes through at 2. Anybody else try to find the absolute minimum? You got what?
I got negative 2.
I understand.
Second trace.
Second trace left down, right down, yes.
Because you have got x minus 3 cubed, and it should be x minus 2 cubed. So you had one of your x-intercepts in the wrong spot. Go again. You had the wrong equation in.
Less down, right down, yeah. Negative 136.
I like that answer. All right, let's try to do the same thing here. Let's identify as much as we can without graphing it. Can we identify the x-intercepts? Where are they? -3, -1. Well, -4 is imaginary. What is this? Like fairy tale land? What do you mean imaginary? So what's different about this factor than the other factors?
Squared inside.
Squared's on the inside, square's not on the outside. So to find those x-intercepts, we would need to set this equal to 0. Right, just like we always do. Well, this would be x squared equals -4. Which means when I square root, what's the square root of -4? 2. So 2 times 2 is -4? Oh, there is.
There's not.
But there is.
Where?
Well, it's kind of 2i. But it's not just 2i. Because I had to take a square root of both sides. Yeah. And what happens every time I have to take a square root? Whenever I choose to take a square root, I have to account for
on both sides.
two possibilities. Okay, let's do this. If I had x squared equals 9. Yeah? And I took a square root. It equals what? Because whenever I choose to take a square root, I have to account for two possibilities. The positive and the negative possibility. So because I chose to take a square root here, I have to account for the positive and negative possibility. So it would be plus or minus 2i are our other two roots. And this, again, this makes sense because think about this. Could I not just take this and write it as x squared minus 9 equals 0? Does this not factor to be x plus 3 times x minus 3? Which means I have intercepts at 3 and negative 3. Anyway. So are these x-intercepts?
Yes.
Yes.
They don't show up on a graph. They don't show up on a normal graph. I would have to have a complex graph, which we don't have. We don't have. So they are, to me, they are not x-intercepts, but they are roots. Because they don't really cross the x-axis. And
Then what are they called?
the paper agrees with me. So the x-intercepts would only be at negative 3 and negative 1. That's the only place it crosses the x-axis.
Then what is that?
What's what?
What's
Two.
the minus
What do we do with that?
Well. Okay. So we know that we should have x-intercepts at negative 3 and negative 1. What's the degree?
3. I don't know. It's 4.
It's 4. So like if you look back through the first example, it was degree 3, and how many roots did we have? How many intercepts did we have on the first one?
2.
Well, we had 2, but one of them had a multiplicity of 2. So we really had 3 total factors, right? If I took it out of the exponent. Look at the next one. It was degree 4. How many roots did we have there? 2, but one of them had a multiplicity of 3. So a multiplicity of 1, a multiplicity of 3 gives me 4, right? Not 4 different ones, but there were 4 roots for a degree 4 polynomial. So this is a degree 4 polynomial. So how many roots would it need to have? 4. But this one has a multiplicity of 1, and this has a multiplicity of 1. So the other 2 roots are here, positive 2i and negative 2i, but they're imaginary roots, right? But it still has 4 roots. But those imaginary ones don't show up on the graph.
What is an imaginary number?
It's when you try to take the square root of a negative. It is very much an allowed thing to do. It's allowed to do. And it gives perfectly good answers that engineers use. That's about as far as I know because I'm not an engineer. I've never done it. Okay? But engineers use imaginary numbers in their calculations. So they're perfectly legitimate numbers. They're poorly named. All right? Calling them imaginary doesn't mean they don't exist. They do exist. All right? It's just because of what our idea of imaginary is outside of math. It's a poorly named number. And it's not something that we can use in everyday math because we can't take the square root of a negative in everyday math. But in more advanced levels, that I've not, past what I do. They're usable numbers, is my point. Sweet. Okay, so this was a degree 4 polynomial. So how many solutions are there to the equation f of x equals 0? There are 4 of them. And we're going to break that down a little bit more. There are 2 real and 2 imaginary. Then it tells us some solutions or zeros can't be seen on a graph. They are imaginary. Explain why the equation x squared plus 4 has imaginary solutions, and what are they? So plus or minus 2i, and why?
You can't take the square root of negative.
No square root of negative number. That's why. All right, so I'm going to go ahead. I'm going to find the y-intercept as well to help me graph this. 3 times 1 is 3. 3 times 4 is 12. And then times a half would be 6. Okay, so the y-intercept should be 6 here. 1, 2, 3, 4, 5, 6. All right, let's talk a little bit about end behavior. Because it's degree 4, I know that the end behavior agrees. Okay? Even power, even degree polynomials have agreeing end behavior. Because the leading coefficient is positive, right? X times x squared would be x to the 4th. Times a half would be 1/2 x to the 4th. But it's a positive number. So because it's positive, I know it's going to go up in both directions. Just like if it was positive x squared versus negative x squared. Right? Negative x squared, they both face down. Positive x squared, they both face up. So this is the same idea, except it's x to the 4th. So I know that they're going to be up here. And so my rough sketch is going to be something like this. All right? I don't know exactly what it looks like. But I know it's got 2 real roots. I know it crosses at those 2 roots. I know that it has to cross that y-intercept. I know the end behavior has to be like this. Okay? You can go ahead and graph it, see what it looks like on your end.
So it's going to look the same as we think it's going to look.
It's going to look similar.
Even though that it has an imaginary number.
The imaginary roots do not show up on a graph. Nothing you know how to graph yet. We'd have to graph this on the complex plane.
What is that?
We're going to do that before the end of the year. We're not doing it yet.
I thought I was smarter by the end of the year.
I hope so. That's always my goal. You know more than you did when you got in here. I got 8 months to get you there. Maybe some of you already got some improvement. I don't know. Maybe not. We'll see.
Yeah, it looks like that.
Does it look just like this?
Yeah.
Very similar. And it's got a little bit of a curve, it looks like, as well on the right side. Okay. So question 5, very important. Can a quadratic equation, you guys know what quadratic means? Degree 2. Can it have 1 real and 1 imaginary solution?
No.
So, you guys have done solutions to quadratics before. When we talk about the x-intercepts that are possible, right? So what can happen when we graph quadratics? You guys remember this? There are 3 possibilities that could happen. It could. How many x-intercepts does this have? So how many real solutions does this have? 2. Okay, what else could happen? It could have 1. What is it like when it has 1?
It's all on the x-axis.
So knowing what you know now, this has 1 solution, but how many real roots would it have? How many real?
2.
2. It's just repeated. It's made it bounce. Right? So this has 2 distinct roots, 2 different real roots. This has one real root, but it happened twice, right? So it wouldn't have any imaginary roots here. Or we could have something like this. So how many roots does it have?
0.
0. But what we learned today is because it's degree 2, it must have at least 2 roots. But none of them are real, which means they both are imaginary. Okay? So we could have 2 imaginary roots, we could have 2 different real roots, or we could have a repeated real root. But it's still 2 real roots. We can never have 1 real root and 1 imaginary. Right? They can't mismatch. Complex roots have to come in pairs. Always. There has to be either 2 of them, or 4 of them, or 6 of them.
Wait, so if it's like that, there's an imaginary root.
There's 2 imaginary roots.
Where?
It depends on the equation. So I just made this up. But like here, this is a quadratic. What would be its x-intercepts? Well, to find the x-intercepts, we would set this equal to 0. So depending on the equation, it's going to be somewhere like this. To have no real roots, that means we have to have shifted the graph up and it's concave up, or shifted down and it's concave down, right? One or the other.
I think we did a quiz this like that last year.
You probably did have to identify how many, if it was 1 solution, no solution, 2 solutions. That's something you normally go over. So, complex roots or imaginary roots come in pairs. Did you guys write that down somewhere? In pairs. It's very important. Why do they come in pairs? Because when I take the square root of the negative, I have to account for plus or minus. Right? Oh, I had something else I want to say. I don't have time. Just move, Cody. All right. Next. So this next one here is kind of just recapping everything we've done and what we know about polynomials. So this is not, like I like this, but this is not my strength is in creating notes, if you've seen that. Like, I never took notes, so I don't do a good job of telling you guys what you need to write down. I just kind of think. So if you guys like this kind of thing, this will probably be good. Polynomial functions have positive integer powers of x. We can find the x-intercepts by setting the y to be 0 and solving. Y-intercepts, we plug in 0 for x to find those. All right? The first real note, like, to me, all these are self-explanatory. Like, I know you may not know them yet, but to find x-intercepts, we plug in 0 for y and solve. To find y-intercepts, we plug in 0 for x. Right? Those kind of go back and forth. This is important, and we kind of talked about it. A polynomial of degree n has exactly n roots, as in zeros. So degree 4 polynomial has to have exactly 4 roots every time. That includes multiplicity. So a root could happen multiple times. Right, so we talked about this before, where it was a degree 4. Our second one was degree 4. One root happened 3 times. The other one happened once. That gave me my 4 different roots. Or 4 total roots. We've talked about different multiplicities. So right here, in this case, p is the root, and p happens k times. So it has a multiplicity of k. Right? P is the root, multiplicity of k. If K is odd, it's going to pass through. If it's 1, it goes directly through. If the multiplicity is 3, 5, 7, 9, 11, so on, it's going to snake through. Okay? Multiplicity is 1, it just crosses. 3, 5, 7, 9, snakes. If the multiplicity is even, it's going to bounce through, but you can see they've made a note. So obviously they saw the test last year too. Right? Where we taught bounce last year, they've changed that. They now say it's tangent to the x-axis. But that just means bounce. All right? It means the same thing. That's just the wording that AP uses. College Board. And so if K is 2, 4, 6, 8, 10, and so on, it's going to bounce or be tangent to the x-axis. And then those are really the only new things we've done. This is review from what we've already been working on this year. Relative max, relative min, right, where we change from increasing to decreasing is a max. From decreasing to increasing is a min. And then concave up is like a cup, concave down like a frown. Holds water, it doesn't, okay, for me. And the point where it changes is called the point of inflection, where concavity changes. Remember, when it's concave up, rates of change are increasing, concave down, rates of change are decreasing. Hopefully you guys are familiar with that. I'm going to hand these to you. I wish I'd had time to let you fill them out in class. But let's just say, let's bring them back. Let's do this first thing. Let's do it first thing tomorrow. Okay? Maybe your other teachers will do it. If you're in multiple dual enrollment AP courses, you just have to fill this out once and put every class on one of them. All right? And if you're not in any others but mine, we'll do it tomorrow, first thing. We'll fill this out.